Covalent bonding, drawing Lewis structures to represent the sharing of electrons inside molecules. In order to accomplish this, first we need to sum the valence electrons for each atom. If we have a polyatomic ion with a negative charge, we would add in an extra electron for a -1. We would add in 2 extra electrons for a -2. If we end up with a polyatomic ion with a positive charge, we would remove an electron because cations have lost electrons. Connect all the atoms with single bonds, and then use the extra valence electrons to complete an octet, or in other words, 8 electrons for each atom. Of course, hydrogen is a very small atom, and it will only end up with a duet, or 2 electrons. If we find we don't have enough electrons to complete all the octets, we'll need to provide multiple bonds, meaning double bond, triple bond, to get double duty out of those electrons. However, beware, we only want to add 1 multiple bond at a time as needed. We'll start with fluorine. Fluorine is in the 7th column of the periodic table, 7 valence electrons times 2, 14 total. So we'll put a fluorine down and we'll arrange 7 electrons using a dot to represent each electron around the fluorine. I'll represent the second fluorine and put 7 electrons around that fluorine, 2 on each side representing each of the 4 valence orbitals, and we'll place the extra electron there. And then we can put these two together to end up with a fluorine molecule. Now it gets tedious pretty quickly, counting all these dots and making dots, and things can get messy, so we could represent each pair of electrons as a line instead, and we can keep our Lewis structures quite a bit more tidy. Even though AP will call these Lewis dot structures, you do not need to draw dots. You certainly may draw lines, so I might instead draw the fluorine molecule this way, which is a little bit easier and tidier. With 14 electrons, I need 7 lines to represent those 14 electrons. Of course, hydrogen with only 1 valence electron, we would bond our hydrogen together using the 2 electrons to produce H2. Let's proceed to oxygen. You know that oxygen is in the 6th column of the periodic table, meaning 6 valence electrons. So we'll draw oxygen, so for a total of 12, we'll draw oxygen with the bond in between the 2 oxygens and distribute the rest of the electrons. 1, 2, 3, 4, 5, 6. Having used up all of the valence electrons, we can see that the oxygen on the right-hand side only has 6 electrons around it, not 8. So we're going to have to erase one of the pairs of electrons on the oxygen that has plenty and put that pair in between, therefore ending up with an octet around each of the oxygens. This would be called a double bond, and these would be called unshared or non-bonded pairs of electrons. It does not matter where you place those. Those pairs of electrons could be here or they could be on this side of the oxygen. That doesn't make any difference. Moving on to nitrogen. Nitrogen, of course, in the 5th column of the periodic table has 5 valence electrons for a total of 10 in the molecule. Connecting the 2 nitrogens, 1 bond, 2, 3, 4. I've used up all 5 now, and we don't have an octet, so we'll go back and we'll need to erase. You, of course, if you can see this coming, can take care of your multiple bonds now. The nitrogen on the right-hand side has an octet, but the nitrogen on the left does not. We'll need to erase yet one more and put the bond in between, ending up with what we would call a triple bond. Let's pause and compare bond lengths. We've seen single, double, and triple bonds. Let's have a look. We have a table here that will show us both bond lengths and bond strengths. We'll look at both at the same time. And what we want to compare is not just any single bond with any other double bond, but we want to compare single, double, and triple that are between atoms that are the same. So a carbon-carbon single, a carbon-carbon double bond, or a carbon-carbon triple bond. We could do the same with a series of carbon-oxygen bonds, single, double, and triple. We could do the same with nitrogen and oxygen, a single and a double. So let's notice in general that if we look at the carbon-oxygen, the single bond is longer with a value of 143 compared to the triple of 113. And these are measured in angstroms, and angstrom is 10 to the minus 10th meters, whereas the carbon-oxygen bond, single bond, has a strength of 358, but the carbon-oxygen triple bond is 1070. That's in kilojoules per mole, representing the energy needed to break the bond. So we can see that while the triple bond is shorter, it's stronger. So to summarize, we can see that single bonds tend to be longer but weaker bonds. Double bonds tend to be shorter but a little bit stronger in terms of the energy required to break them. And lastly, triple bonds are generally the shortest and the strongest. Now that's not to say that any triple bond is always shorter than every single bond. As a comparison, I've represented the hydrogen single bond, which of course is much shorter than a carbon-nitrogen triple bond because the hydrogen atoms are so small, the atoms are able to scooch close together, representing or producing a much shorter bond than even this triple bond. Of course, a whole lot shorter than a single bond of two larger atoms. Moving on to more Lewis structures, let's take a look at the carbon, two hydrogens, and fluorines. Looking at the valence electrons, we end up with 20. We'll put the carbon in the middle, and a fluorine around it, and another fluorine around it, and a hydrogen and a hydrogen. Having used up 4, I'll carry on with unshared pairs 5, 6, 7, 8, 9, 10, and that would represent the 20 valence electrons available. Moving on to water, which has two valence electrons from the hydrogen, 6 from the oxygen, for a total of 8. Put the oxygen in the middle, hydrogen on each side, 3, 4. There's our 4 pairs of electrons, or 8 valence electrons total. Now we see an ion, the cyanide ion, carbon with its 4 valence electrons, nitrogen with its 5, and this extra electron here is a result of the negative charge. That extra electron, of course, would be coming from perhaps a sodium that has donated the electron or given up its electron and becomes, say, sodium cyanide. So let's draw this carbon connected to the nitrogen, and you would see with 10 electrons we're not going to have enough to go around. I only have 2 more to distribute, and if I distribute those in the middle, I'll end up with 10 total, and the carbon having an octet and the nitrogen having an octet. It's standard practice in chemistry that if you are drawing the Lewis structure of an ion, is put that ion in square brackets to alert your reader that you've got an ion, and show the charge outside the square brackets. And now the nitrite ion, with its 5 electrons for nitrogen, 6 each for the 2 oxygens, and the 1 extra from the negative charge. So we'll put nitrogen in the middle with an oxygen on each side, and fill in. We've got 2, 3, 4, 5, 6, 7, 8, 9. And you can see that while each oxygen is satisfied or has an octet around it, It's easy to miss, but we should notice that the nitrogen in the middle does not have an octet. Therefore, we needed multiple bond. So we'll take off of one of the oxygens, it doesn't matter at this point which one, and put that in between as a double bond, ending up with an octet on the oxygen on the right hand side, an octet around the nitrogen in the middle, and an octet around the left hand oxygen. We should of course put this ion in square brackets to represent that it is an ion with the charge outside. Finally, here's some rules to help guide us when we were drawing Lewis structures, and sometimes the order can help us. Often the central atom will be written first. That's not always true. Of course, we write water as H2O. Perhaps we really should be writing it as OH2, but we're not about to change now. We'll find hydrogens and fluorines terminal, meaning on the outside of molecules. Generally, we're not going to bond oxygens together, except of course in the oxygen molecule itself and in hydrogen peroxide, or in peroxide molecules, you'll find that the oxygens will bond together. Carbons will often bond together and are on the inside, avoiding being terminal atoms to avoid having unshared pairs. Down below, we'll notice that we have this acronym HONC 1, 2, 3, 4. This is to represent that hydrogen will have one bond, oxygen tends to have 2 bonds, nitrogen tends to have 3, carbon 4. Now that 3 bonds for nitrogen could be a double and a single. The 4 bonds for carbon could be 2 doubles. And what's represented up here would be unshared pairs. We generally find one unshared pair of electrons around a nitrogen, and we'll generally find 2 unshared pairs around oxygen. A few more Lewis structures. AP will often help out by providing an arrangement of the atoms. So we can see that HNO2, which is nitrous acid, has 1 valence electron from the hydrogen, 5 from the nitrogen, 12 total from the oxygen for a total of 18. We'll fill those in with 1, 2, 3, 4, 5, 6, 7, 8, 9. And we find out that we are coming up short with that last oxygen. You may have put your bond originally on that last oxygen and said, whoa, my nitrogen in the middle is coming up short. Either way, we're going to have to end up with a double bond, and we'll put that in between the nitrogen and the oxygen so that all of the atoms have an octet. Next we have ethanol. Ethanol, 2 carbons, ultimately 6 hydrogens and an oxygen for a total of 20 electrons. And we'll fill those in 1, 2, 3, 4, 5, 6, 7, 8. Let's not forget the unshared pairs, 9 and 10 around the oxygen. No double bonds necessary. And notice that we have observed the HONC 1, 2, 3, 4. Both of our carbons have 4 bonds around them. Hydrogen's 1 bond. The oxygen with its 2 bonds and its 2 unshared pairs. 2 unshared pairs, you can see them here. Finish with ozone. O3, 18 electrons. Let's bond 3 oxygens together, and we'll end up with 2, 3, 4, 5, 6, 7, 8, 9. And we find that this oxygen on the left-hand side does not have an octet, and so we'll need to take an electron pair from the central oxygen and form a double bond.